Welcome, folks. In our next video about fields, I want to give a sort of longer description. So fields, if you'll remember, are things like the real numbers, the rationals, the complex numbers, or the integers mod p, where p is a prime. So we've already worked a little bit with this condensed definition. A field has two operations, addition and multiplication. And the entire field has to be in a abelian group under addition. Let's call the additive identity 0. If you remove 0 and you consider all the non-zero elements, that needs to be an abelian group under multiplication. Finally, we have one rule that tells how multiplication and addition relate, which is this distributive property. A times B plus C is equal to A times B plus A times C. This condensed definition it requires a little bit more maturity, right? We're using words like abelian group. And in this class, we're just learning about abelian groups for the first time. So students often prefer this expanded definition to start. So let's look at this. A set F is a field if it is equipped with two binary operations, addition and multiplication, such that for all elements A, B, and C in our field, we have the following properties. Associativity of addition, you can move around parentheses, and associativity of multiplication, commutativity of addition, and commutativity of multiplication. You have to have an additive inverse, which we call 0, and an additive identity, which we call 0, and a multiplicative identity, which we call 1. Notice I didn't also need to specify that 0 plus A is equal to A, because that's implied by commutativity, right? By commutativity, I know that 0 plus A is equal to A plus 0. And I just told you that A plus 0 is A. So in a sense, I've already told you that 0 plus A is A. Inverse is, for any element A in our field, there's some additive inverse such that when you add A to its additive inverse, you get the additive identity 0. Now, not every element has a multiplicative inverse, but every non-zero element has a multiplicative inverse. So for every non-zero element A, there's some multiplicative inverse, so that A combined with its multiplicative inverse is the multiplicative identity 1. And again, I don't need to specify that A inverse times A is equal to 1, because commutativity specifies already that A inverse times A is equal to A times A inverse, which I've told you is 1. And then, of course, we have the same distributivity property. So hopefully you can see how these definitions line up. They're really just two ways of phrasing the same exact thing. So associativity is part of addition being a group, and multiplicative associativity is part of the non-zero elements being a multiplicative group. Commutativity of addition and multiplication comes in here. We have an abelian group under addition and an abelian group under multiplication. Identities just come into having a group under addition and a group under multiplication. Inverses, okay, inverses relate to having a group under addition. And for multiplication, you'll see that we only required the non-zero elements to have inverses, because we only needed a group under multiplication for the non-zero elements of our field. And distributivity is sort of copied over exactly. Any questions about these definitions and how they're the same? All right, thanks so much.